All right, so 9, you were rolling dice. All right, so A1 was 1 or 2 on the first roll, A2, 3 or 4 on the second, and A3, 5 or 6 on the third. And then they tell you the different probabilities. And basically, they just wanted you to play around with the different formulas that we have for unions. So if you have a probability of a union, no matter what you know about A1, A2, or A3, if you have a probability of a union of 3 things, how can you rewrite that? Okay, A1, A3, okay.
Yeah, and then you add the intersection of all.
Good. Whew. All right, cool. Okay, so they tell you that they give you the different pieces of these things, right? Because they tell you these individual probabilities here and this one as well. Yeah. So if we go through the different pieces, well, what's the probability of each of the A1, A2, and A3? A third. And then they tell you that the intersections are going to be a third squared. And they tell you the last one was a third cubed. Yeah. Okay. We're going to talk about why those are true in a couple of sections from now, why those intersections are the way they are. But in particular, we can kind of think about it now. A1 was rolling a 1 or a 2 on the first roll, and A2 was rolling a 3 or a 4 on the second roll. Does what you roll on the first roll have any effect on the second roll? No. So what you end up doing is just multiplying the two probabilities together in that case. We refer to those types of events as independent. If one event has absolutely no effect on the other event, okay, you can do the probabilities with multiplication, as long as they can occur at the same time, I should say. All right, so now it's just a matter of simplifying it in the form that they wanted. All right, I think I said it was 1 minus the quantity, 1 minus a third cubed, right? Yeah. Okay. Well, that part's your 1. Agree with that? All right, so then we want 1 minus a third to the third power. So let's see. Can I do them? I mean, you could actually literally just do the arithmetic if you wanted to. I was just trying to see if I could be clever with it. If I look at that piece, I can certainly factor out a 1/3 squared out of each piece. And if I factor out the minus sign with it, that would change all those to pluses, right? Is that even going to be very helpful to me? I was just trying to think if it would even be helpful to do it that way. Like I said, it might just be easier to do the arithmetic. 1 minus a third cubed. I just want to make sure I get to the right answer when I'm done. That's going to give me a 3 and then minus a third. So I've got 3 of those in there. Not too worried about the arithmetic, honestly. I was trying to be clever, but my cleverness is not working very well. 26/3. Yeah. And then if I actually multiply those two things together, I get 26/3 cubed. This is a lot more work than anybody should ever put into this, by the way. Yeah, it's making a mess more than anything. Anyway, you should get what you want if you just do the arithmetic, right? Because if you just check to make sure that this really is equal to the 1 minus 1/3 cubed or the 2/3 cubed, you'll be done. I was just trying to play around with the algebra. Like I said, it's a lot more effort than what I really wanted to put into it. No, no. The theorem that you want to use is this one, and it's just a matter of plugging the things in and showing the same thing. That's perfectly fine. Sorry, I thought I could be a little bit more clever, but it's not working very well. Which is okay. It happens. I'm not getting 2/3 out of that. I may have made an arithmetic error myself somewhere along the line. Anyway. You can, this part right here is 1. If you can show that this part is 2/3 cubed, you're done. Is basically what you have. Because it was 1 minus the quantity, 1 minus 1/3 cubed. So if you simplify this, you should get, what, 8/27? Is that right? It would be 2/3 cubed, so you could get 8/27. Yeah. Yeah, because you got the 1 here, so I'm just saying this should be a minus 8/27 when you're done. That's 1/27. And that's 3. That's the 3rd, isn't it? Maybe that was where I was trying to work too hard at it. That would make my life a little bit easier if I do it that way. If this part is, let's do it this way. I'll try one more time. And then if I don't do it nicely, then we're going to quit. That? Because that's a 9th and a 9th and a 9th. So it'll simplify to a 3rd. Yeah. And what do I want to do from there? Like I said, I'm trying to be clever, but my cleverness is escaping me right this second. Which is that? Because I factored a 3rd out of both terms. Oh well, I'm gonna get the number that I know it's supposed to be. That's 8/9. Because it's 1 minus a 9th. I could have just simplified it to start with. Like I said, I'm not being very good about making it clever, but 8/27 is 2/3 cubed, which is what you were trying to get to. Anybody else more clever about doing it than I was? Or did you just simplify it? Or you don't want to tell me until I grade it? The point of the problem was you doing this and playing around with that and plugging the pieces in. I don't care about the cleverness and simplifying your arithmetic. That was not the point. Other questions? All right. Well, let's continue on with our counting argument stuff that we started last time. This was the problem we worked on last time, right at the, I believe it was the last thing that we did last time. Okay. So, what I want to look at, going back to this problem, we talked about first counting the number of total selections. We used combinations in this case, mainly because if you pick a group of 5 people, and you just want that group of 5 people to do something, it really doesn't matter the order in which you pick them, but you do want to pick different people, right? So I wouldn't do 10 times 10 times 10 times 10 times 10 because I can't pick the same person twice. And so I wouldn't use just the straightforward multiplication principle in that case. So we used combinations rather than permutations because the order didn't matter, and then got our 252 there. But what I want to notice about this group of 10 is that it's actually split into two different groups, right? We got a group of men and a group of women split into two distinct groups, and then this problem asks us to pick some men and some women, some from group 1 and some from group 2. Let's look at the next problem on the sheet here. And we flipped from picking from a group of men and women to a group of marbles. Some are black and some are white. But it's essentially the same setup, right? We're going to pick a group of marbles without replacement. Remember, without replacement means that something cannot get selected twice. Okay? The same idea, we're going to pick a group of 10 marbles at random. And then it asks us, what's the probability that X of them are white, right? For whatever those X values happen to be. But notice it's the same idea. Notice that if we go back up here to the previous example, notice it says, we'll have 3 men and 2 women. Well, if I told you it was a group of 5, and we had 3 men, then you know the rest had to be women at that point, right? If I would have said pick 4 men, we would have had 1 woman, right? And it has to make up the difference. So if I go back to this next example, if you're going to pick X white balls, how many black are going to have to get picked? So if we're going to do X of the 10, if we're going to do X of them, how many would you have? 10 minus X, right? The rest is going to have to make up the rest of them, okay? So if we want the size of our sample space again, let's do that first, get our denominator. We want the size of our sample space. How many balls are we selecting? How many marbles are we selecting? 10, and out of a group of 25. So how many, and you're doing it without replacement. And again, you're just grabbing a group of them, so the order is not going to matter. So how would we compute that? 25 choose 20. Good. Good. I'm not going to worry about simplifying that number. It'll be a big number. Main reason why I'm not going to simplify it. Okay. All right, so now we need, this is going to be on our denominator, right? We want the probability that X of them are white. This will be our denominator. If we want X of them are white, how many ways can you choose X white balls, white marbles? How many white marbles do you have to choose from? 10, and you're going to choose X of them, right? So it'll be 10 choose X. What does the rest have to be? How many black balls are you choosing? 10 minus X. And how many black balls do you have to choose from? 15. And again, we'll multiply those two numbers on the top because we're calculating the number of ways this can happen. We can think about dividing this up into tasks. First, pick your white balls, then pick the black ones. Right? And whatever the X happens to be, we can just plug that in and figure out the number. Notice that your X has to run from 0 to 10 because we're only picking the total of 10 balls and only 10 of them are white anyway, right? So I can't pick 11. I can't put in 11 for X, for example, or a negative number in for X. This particular, notice that this changes depending on what the X is. So in the next chapter, we're going to start talking about different types of what are referred to as probability distributions, especially in the discrete case. This is an example of what's known as a hypergeometric distribution. I know, a long word. We'll come back to that definition later. But the idea is we've got one big group divided into two small groups, exactly two small groups, and you're going to pick a certain number out of one, and then the rest will come from the other. That's what a hypergeometric distribution looks like. What we're going to do later on is we're going to collect a bunch of different types of distributions, and we'll want to know what one to use depending on the scenario we're given. So in this case, one big group, within it is two small groups, and we're choosing a certain number out of one of the groups, and then the rest comes out of the other. We'll come back to that. Are you okay with getting this set up here, this part? Not too worried about this words yet. Okay. Like I said, this is section 2.5, so we got a little bit to go. Yeah, Kevin.
So if they ask us about one part, also
Yep, we'll multiply them together if there's other groups. Yep, if there's more than two. Yep, we'll multiply them together. So I think the next example actually does that. Yeah.
Is it because the events are independent? Is it that way we look like?
It's because we can think of them as tasks. Independent is another way to think about it. We can think about it as tasks. I gotta pick some white ones and I gotta pick some black ones. So I first pick the white and then pick the black. Yeah. All right, so this one's a little bit different because rather than having two different sets of things, we have three different sets of things, right? So let's first worry about how many ways there are to pick. Oh, actually, this is with replacement. This is how many different ways are there to pick the three balls. So notice this one, in this case, it's drawn at random with replacement rather than without. So if I see it with replacement, are we going to be able to use combinations? No. Okay. So again, we're going to select three balls from a group of 10. So what's the size of your sample space going to be? How many ways do you have to pick the first ball? And the second one? And the third one? 10. So it'd be 10 cubed, right? It's with replacement. So we have 10 ways to pick the first ball, 10 ways to pick the second ball, 10 ways to pick the third ball. So we just need to multiply them all together, and we'll get 1,000. Yeah? Okay. Now we need to figure out the event. We want all the balls to be different colors. Well, we're only picking, this was a little bit, probably fairly straightforward. We just have to be a little bit careful. We just want to make sure that they're all different colors. Well, if we're going to pick three balls, what does that tell us? If we're going to want all three to be different colors, what do we need to do? What do we need to choose? One of each, right? Because we're only picking three, right? The problem would get harder if we had more than three that we were picking. Make sure there's at least all different colors that can go through a lot of different scenarios, right? But this one's pretty straightforward. We need to pick one white, we need to pick one red, and we need to pick one black, correct? So let's think about ways to select one of each color. How would we compute that? We're going to select one white, one red, and one black. Yeah, just.
Would it be 5/10 times 3 times 2?
Okay, so right now I'm just counting the number of ways, but you're thinking about the probability correctly. I got 5 ways to choose the white, right? Three ways to choose the red. I can talk, and 2 ways to choose the black. But remember, this is just using a straightforward application of the multiplication principle, right? Pick a white, pick a red, pick a black. But notice it doesn't say the order, does it? Okay. This literally would be white on the first, red on the second, black on the third. But all we care about is that they're all different colors. So you could do red, white, black, black, red, white, right? You could flip them around. Now, would the numbers change, though? The multiplication? No, because multiplication is commutative, right? We get the same number each time. So how many ways would there be to rearrange those things? Why is it 6? You're right. It's 6 instead of 3. Why is it 6? It'd be a 3 factorial. We rearrange it, right? So we'd also need to multiply this by 3 factorial. Okay. So this part here is white, then red, then black. This would be the number of rearrangements of the 3 colors. Oops. Since we're not doing something with a combination, and we're just counting total number of ways, we really have, for example, in this 1,000 here, we've considered the order, correct? In this 1,000 ways, there's white, then red, then black. There's red, then white, then black. Right? And all sorts of the other 4 ways to do that. So I have to be, of course, also in here are 2 whites and a red, 2 reds and a white, and all those things. But we've put an order in there. When we do remember the multiplication principle says task 1 followed by task 2 followed by task 3. There's an inherent order there, correct? So when we did 5 times 3 times 2, that's white followed by red followed by black, but we also want to count red followed by white followed by black, right? And so on, and the other 4 possibilities. Okay. That's why we need to put that extra 3 factorial in here. That's rearranging white, then red, then black. So if we want to make the probability now, we would just make the fraction. So your probability would be 5 times 3 times 2 times 3 factorial over that 1,000 to that 10 cubed. And again, I don't care if you do the arithmetic or not. If you were doing this for some sort of certification exam, whether that was an education certification exam or an engineering certification exam or an actuarial certification exam, you would have to simplify it because those are typically multiple choice. You figure out which one it is. Okay. For me, this is fine. This tells me you understand how to do the problem. As a matter of fact, if you wrote nothing else on the paper and just wrote this would tell me you understand how to think about the problem and see your thought process and just that answer. This one okay? Notice this was, even though it's set up with replacement, that automatically makes it not hypergeometric. This would also not be hypergeometric even if it were without replacement because I've got 3 different categories and not 2. Hypergeometric is literally one big group separated into 2 smaller groups. Okay. All right. Let's look at this one. So again, here we've got one big group, but again, we're divided into 3 smaller groups. We've got a big group of 100, and we're going to select 5 policies from that group of 100. So without worrying about what the problem is asking you to calculate for probability, the overall thing that you're doing is selecting 5 from a group of 100. So what would the size of your sample space going to be? So again, we're choosing 5 from a group of 100. We're going to do this without replacement, right? Because we're going to select 5 different policies. So what's the size of your sample space going to be? 100 choose 5? Good. Again, whatever that number turns out to be, I don't really care if we simplify it. But are we okay with why the size of the sample space is 100, choose 5? That part okay? All right. Let's figure out if we can, let's see if we can figure out what the probability is. There's two ways to do it. The first way we're going to do it is the way that I think it's a lot of times better to think about. In general, when you see some certain keywords here, the keywords that I'm looking at in this case is that. Now, in this case, we could enumerate it pretty quickly, but in general, if you see something that says at least one, that's usually typically a harder thing to count directly. Because think about what at least one means for us here. At least one could mean one from the underwriting class, one from the standard, one from the rated, right? Or 3 from the rated. But it could be 1, 2, 2, right? It could be 2, 1, 2, 2, 2, 1. Right? There's all sorts of different ways that you could do it. You can enumerate it because it's not that big of a set here. You could enumerate it differently. But generally speaking, if you're doing at least one, there's lots of different cases that you could possibly get to. And it just makes it more difficult to try to separate them into the different cases. In this case, I think it's easier to get at from doing the complement, because the complement of at least one is none, right? So we still have to divide it into cases, but the cases are a little bit easier to get at. We could say there are none from the preferred and only from the other two. We could say that there are none from the standard, or we could say there are none from the rated, right? And just delete out those categories, okay? So what if we said there were none from the preferred? Guarantee that there are none from the preferred. How can you guarantee that there are none from the preferred? You 30 choose 5, right? Because we delete out the 70 that we're not going to choose from. That guarantees there are none from the preferred, right? Agree with that? If you want to do none from the standard, what would you have? 75 choose 5. And if you had none from the rated, what would you have? 95 choose. Oops. Now we have to be a little bit careful with this too. Why do we have to be a little bit careful? Is there any overlap among these things? Yeah, there's some overlap, right? For example, I could have none from the preferred and none from the standard at the exact same time, couldn't I? That would just be that they all came from the rated. Right? Or I could do these two at the same time, they all came from the standard. Yeah? Or like with the they all came from the preferred and they were neither standard nor rated, right? So I have to be a little bit careful. This is going to have some overlap. So how can I take care of that? How can you take care of your overlap? Or maybe count it a different way even. Apparently, I'm asking a good question. Since no one's answering me.
You subtract off when you only pick the one group.
Okay, so we said that this included what? If we said they were none from the preferred, they may be all. They may also be none from the standard or none from the rated, right? And then likewise for the other ones. Okay, so how can we get rid of the overlap?
Multiply the chance that it's in those other ones.
What do you mean by multiply by chance?
I don't know exactly, like include, I guess that would help.
Okay. So this one means it's, let's think about it this way. This one means it's standard or rated, correct? So it's a union, isn't it? Right? So how could we do that? If we think about it as a union, maybe you go that way. Yeah, so you subtract the intersection, right? So that 30 choose 5 that we have there really can be thought of as those two pieces. I think we can probably get that 30 choose 5 in a different way. But the idea here is that I need to make sure that I'm not double counting. All right, so this would be, let's make sure we could also, just want to make sure I do this the right way. So this includes only the rated, right? It could also includes only standard, but I'm thinking about going to the next step here. This would be standard or rated, but it also includes the things that are only rated. This one would include only rated as well, which I've already counted here, haven't I? So if I said at this one, I guess I should say, and only standard. I'll put that here. Okay. This one here, this one would include only preferred, which we haven't done at all yet. But it would also include only rated, which we have already counted, isn't it? Haven't we? So at this point here, rather than doing 75 choose 5, what could we do instead? What do we really need? Just need to add back on again. What's the only things we haven't counted? Yeah, it should be the only preferred, right? Is that what should be the ones that we only want to do, right? This one, we've all in this group here, we've already counted the things that are only standard, right? Because it's possible to select all standard and no rated, and it also includes the only rated, and then a mixture of the standard and rated, right? So I'm just trying to make sure that we only count what we need to count and not double as we go along. So at this point, this would include only preferred and only rated. I don't want to put in the only rated though, right? I want a mixture or the only preferred, but I don't want the only rated out of that, do I? I don't want to include that. So what could I do instead? What could I do with that number? That would be the total of only preferred. And, well, sorry, none from standard. So you have some preferred, have some rated. Maybe it's only preferred. Maybe it's only rated. Yeah, we can subtract out the 5, choose 5, the one that we've already done, right? There's only one way to do it, but that would be one way to do it, right? That's already been counted. Yes. This would be, since we've already counted in the first one, I don't want to count it again in the second one. Right? I don't want to count them again. I want to take it out. Now, this one certainly doesn't have any standard in it, so anything that's counted in the 75, choose 5, as long as it's not only rated, we have not counted it yet, right? So we can take that one out. What about this last one? Well, last one's a little bit trickier. Might have been just as easy to enumerate the other cases. It's probably a better way to think about it, too. Usually in these problems, there's more than one way to think about it. Okay.
This one is the minus 2 times 5 choose 5.
Okay, so we would, well, notice this one's not going to include any rated ones, though, right? We've already removed the rated ones out of this one because it says that none of them are rated. I do need to subtract some things out. What is that made up of if it's not rated? Yeah, it's made up of preferred and standard. What's already been counted in the first one? Only standard. This one's already counted only preferred, right? So what would we need to subtract out if we've already counted those things?
25 choose 5, 70 choose 5.
Yeah, I need to subtract out the 25, choose 5 to get rid of the standards, and the 70, choose 5 to get rid of the only preferreds. Right? Yes?
Wait, so that at first we did 5, we subtracted 5 choose 5. Then there we subtract.
This part right here, that represents the group that's only rated. They're all rated. I mean, only rated is not the way. These are all rated policies. I've already counted that up here. I don't want to count it twice. Okay? This is the ones that are only standard. But I've already counted that here. So I don't want to count it twice. These are the ones that are only preferred. But I've already counted that here. So again, I don't want to count it twice. So that's why I'm subtracting those out. So that's the subtraction of doing that intersection piece, right? We want to make sure we're counting, not double counting things. Like I said, there's probably a way to think about it a little bit faster. But this would get rid of the overlap pieces. Counting's hard, generally speaking. There's a whole field of math devoted to counting called combinatorics. It's hard. Because you got all these cases that you have to worry about. Someone I went to graduate school with did something that was basically counting, and she had to eliminate 168 cases of things. And through all this combinatoric argument stuff. I didn't say it was necessarily fun, I just said it was hard. There's a lot of different things to be able to count things. All right. So anyway, when we're done, these are the things that we don't want, right? So if you were making your probability, I would start with a 1 minus because these are the things that we did not want, correct? We had that, what was it? 30 choose 5 on top, a 75 choose 5 on top, a 95 choose 5, on top. But we also need to subtract off the things that we double counted. And then divide by that. And maybe if you go back and think about this problem, you might think of a different way to do it that's more straightforward than this. But I think we're good as far as we've counted now, right? This counted. Let's just make sure that we are happy with what we have. Everybody seemed okay with the denominator. We understand why I'm doing 1 minus, because we did the complement, right? This was no preferreds, but the preferreds counted the things that had a mixture of standards and rated, but it also had only standard and had only rated, right? Coming to the next one, this had a mixture of preferred and rated, but we've already counted only rated. So that was where this -5, choose 5 came from. Making sure we didn't count that twice. This one was a mixture of preferred and standard, but that we've already counted over here only preferreds, and we've already counted here only standards. But we don't want to count it twice, so we subtracted off those possibilities. So that should give us our numerator. Is that okay? Everybody seems super happy about it. What if you did it well, this one, we thought about doing the complement because of that at least one idea. What would have been another way to do this if we would have done it kind of just straightforward, if you will? Well, we could have had, again, we had preferred, standard, and rated were the 3 possibilities, right? We want at least one from each. So one possibility could have been 1, 1, 3, right? Another possibility would have been 1, 2, 2. Another possibility would have been 1, 3, 1. That gives you the possibilities of having exactly one preferred, right? We could have also had 2 preferred. That would have been 1 standard and 2 rated, or 2 preferred, 2 standard, 1 rated, and that's the only possibilities there. Or you could have had 3, 1, 1. So you would have had 6 cases to count up. So again, notice these are exactly each of these, right? That's why I broke them into the cases. And we have mutually exclusive cases, so that when I get the total, I can just add them up. That's the idea, right? They're mutually exclusive. Okay. You see where these are the possibilities, right? Exactly 1 preferred. I can do 1 standard, 3 rated, 2, 2, 3, 1 that way. And notice that the other ones are kind of mirror images, right? If you had 1 standard, you could do 1 rated, 3 preferred, or 3 rated, 1 preferred. We've already counted, and then 2 and 2 for the others, and likewise. And then at this point, you could just do your combinations and multiply. This would be 70 choose 1 times 25 choose 1 times 5 choose 3. Pick 1 preferred, pick 1 standard, pick 3 rated. What would the next one be?
70 choose 1, 25 choose 2, 5 choose 2.
And then likewise all the way down, right? Keep going, and then at the bottom, total them up. I'm not sure either way was easier in this case. Again, there's multiple ways that you can think about these problems. That was kind of the point of this. Then I wanted to make your heads hurt for a few minutes, apparently. Did I succeed? Okay. Good. All right. One of the things, though, is helpful with these problems is being able to break them into cases. So that was kind of the point of this problem. Don't worry, there's not going to be one that's harder on the exam. Probably question number 1. Ready? And make me do this on the exam. No. However, there might be ones where you have to break into a couple of cases, or ones that you may have to count out, subtract out an overlap, which this one does too. All right. Questions on that one before we move on to the next one? Yeah.
So I forget all the cases I've been
you're going to add them up because we've split them up into it's this or this or this or this, and there's no overlap. So we would just add in that case. And then divide by the total. Yep. Divide by the total. Yep, that's right. Okay. All right. This one has also got a little bit of a challenge to it. So let's chat about it for just a second. We've got 27 pieces of luggage, and you've got a typical luggage handler that just goes in and smashes for it. The problem in this case is, what's the probability that exactly 2 of the 4 are insured? Notice in this case, this is another hypergeometric. We've got a selection of luggage where we've divided it into 2 pieces. Some are insured, some are not insured. Okay? So this is another, and we're going to select a random sample of 4. So we're going to select the luggage without replacement, right? We're going to damage 4 of them, not the same one 4 times. Okay? So this really is another example of those hypergeometric things, right? So in particular, what would your denominator be for your probability, without a doubt? 27 choose 4, right? You've got 27 pieces of luggage. You're going to choose 4 in the denominator. The issue is, on top, I know I'm going to divide it into 2 pieces. We're going to pick 2 insured and 2 not insured, right? We're going to separate it into 2 pieces, just like we did the other ones. What's the issue? I don't know to start with how many things are insured, right? So we've got to figure out what these 2 numbers are up here. I got to know how many insured there are and how many uninsured there are to be able to fill in the rest of this. So all we did all right here comes from, the denominator comes from that sentence, and the numerator comes from that sentence, right? From a group of 27, we're choosing 4. That's how I got the denominator. Calculate the probability of exactly 2. That's where this numerator is coming from, but I don't know how to fill in these gaps yet. I don't know what those numbers are because I don't know how many are insured or how many are uninsured. Now, using kind of a tried and true principle of what you know from pretty much every math class you've ever had, are you typically given information you don't use? No. Okay? So what haven't we used? This middle sentence, right? Okay. So let's first set up an equation from the middle sentence. The probability of exactly 1 piece of luggage being insured, one of the damaged pieces, is twice the probability that none of the damaged pieces are insured. So not worrying about how to calculate those probabilities yet, what would be a mathematical sentence to say that? Probability of the 1 piece being insured is twice the probability that none are insured. What would be a mathematical equation, a mathematical sentence we could make from that, not calculating the probabilities yet, just literally a sentence, or a mathematical sentence from that English sentence? So we equal sign in the middle to start with. Okay, so what's y and what's x? You're right, that's the equation I want. What's the y and what's the x? Okay. Yep, so the probability of exactly 1 is 2 times the probability of exactly 0. And this is pretty typical notation that we'll use later on in the next chapter. We'll typically use x to represent a quantity that we're trying to measure with a probability. So this is pretty typical notation that we'll use later on. Okay. Probability of exactly one being insured is equal to 2 times the probability that none are insured. Okay? All right. So let's think about how we can figure these probabilities out. Well, same concept that we had, because above, if I think about this using the same notation, this is the probability that 2 are insured, right? So the same notation. We agree? Okay. So let's do the right-hand side first, and then we'll do the left-hand side. What's the denominator going to be? 27 choose 4, right? I don't know how many are insured, so I'll call it, say, I. We'll use a little I. I don't know how many are insured, right? How many, on the right-hand side, how many insured ones do you want to pick? 0 of them. If I of them are insured, how many are not? Or, sorry, yeah. If I of them are insured, how many are not insured? 27 minus I, and how many of those do you want to pick? 4. But you can figure out what letter we're going to solve for. You solve for the I, right? And the I is what's going to go up here for the insured. Okay? So we're going to set up an equation to solve for the I. Okay, so what does the left-hand side look like? Again, what's your denominator? 27 choose 4. What's your numerator?
I choose 1. 27 minus I choose 4.
Good. We have an equation to solve. Yes, Kevin.
Could you repeat again what you just put I?
Because I don't know how many are insured. That's what I need to figure out. Because the number of insured is what's going to have to go up in here. Say it again.
They told us that 2 are exactly true.
No, the probability that the 2 of the ones you select are insured. I don't know how many total are insured. All I know is that of the ones that we're going to damage, 2 of them are insured. That's why it was in the bottom of our choose. All right. Yes.
Why is the 2 not on the other side?
It says the probability that it's equal to 1 is twice the probability that it's none. Isn't that what it says? Or does it say it the other way around?
No, that's it.
Is that what it? Okay. So probability that exactly 1 insured is the price that well, let's double check and make sure that's what it actually says. Yeah, probability that exactly 1 is a piece of luggage is damaged. So that's the probability that is equal to 1 is twice the probability that none are. That's why the 2's on that side.
Yeah, I'm saying that the probability with exactly 1 damaged piece is 2 times the other.
Right. That's what I have, isn't it? Probability that 1 is damaged is 2 times the probability that none is damaged.
Oh, yeah.
No, you're fine. That's okay. I was making sure I wasn't reading it wrong. But it should be this way. We'll find out in a second because I know what the number is supposed to be when we're done. So, all right. Looking at this equation, does something go away pretty quickly? Yeah, the 27 choose 4 is on the denominator on both sides, right? So if I multiply by it, it goes away, doesn't it? Okay, cool. All right, let's see if we can simplify a couple of these really quickly, and then we'll use the formula for the other. Let's look at this one first. The I choose 0. Let's not worry about formulas. Let's just think about it. From a group of, doesn't matter, let's say from a group of 10 things, how many ways are there to choose none of them? Just 1, right? If I don't choose anything, there's only 1 way to choose nothing, right? So what's I choose 0 going to simplify to? 1. So that might as well just go away as well. Let's do the other one on the other side. Pardon me. From a group of let's say a group of 10 things again. How many ways is there a way to choose one? 10, right? So from a group of I things, how many ways are there to choose one? Just I. So that's going to simplify to I. So this will just be just an I here. Okay. All right, so now let's use our formula. So remember that the formula is top factorial, and then it's so remember the formula for n choose r is n factorial over r factorial times n minus r factorial. That's our formula. So I'm just applying that formula to both sides here. To simplify each of those. So on the left-hand side, our fraction is 27 minus I factorial over 3 factorial times 27 minus I minus 3 factorial, right? The difference between the two. Same thing on the other side, it's instead of a 3, we have a 4. Now looking at the equations again, do you see anything else that goes away pretty quickly? Yeah, the 27 minus I factorials go away, don't they? Okay. So those go away. Let's just cross multiply a little bit. I'm going to leave the. Okay, let me simplify it a little bit before we cross multiply. I've got I times 1 over 3 factorial. This is 24 minus I factorial. 2 times 1 over 4 factorial. 23 minus I factorial. Let's do this in pieces. Let's clear this out of the denominator first. That piece right there. Let's use this has a laser pointer option. This part right here. Okay, those went away. This nice little laser pointer option. I just wanted to use it for fun. What if I multiply both sides by that? Well, if I multiply this to the other side, you'd have 4 factorial over 3 factorial. What does that simplify to? 4, right? So I'd have a 4i on this side. Let's move this one. If I move this to the other side, I'd have, let me write it off to the side. You'd have 24 minus I factorial over 23 minus I factorial. What's that going to simplify to? 24 minus I, right? Because remember, factorial, you start here and you start subtracting by 1 each time. Well, if I subtract 1 off there, I get what's on the denominator, don't I? And then they're all going to cancel. So on the right-hand side, you'll have 2 times 24 minus I. That's a lot easier equation to solve, isn't it? I believe you'll get I as 8. But distribute your 2 through. Add your 2i and divide by 6. So we get that 8 of them are insured. Now we can finish the problem. Going way back up to the top where we set everything up. What numbers do you put in the tops now? How many are insured? 8. How many are not insured? 19. Yeah. So when I multiply this to the other side, you'll have 4 factorial over 3 factorial, which simplifies to 4. Because I'm taking this and moving it over here. And so I just get a 4. So that's where the 4i comes from. And then I'm taking this and moving it over here. So I'm just left with 4i. That's where that came from. That one okay? Yeah, just. Oh, up on top? Yep. There you go. Yep. We needed the I to fill in the tops. We already had everything else written down. The hard part was figuring out what the I was. All right, questions on that one? It wasn't as bad as the previous one, I don't think. All right. I'll leave the last one there for you for practice. It should look like one of the hypergeometric ones. All right. What's it?
Can I see that? There.
This one?
There.
Where do you want me to stop?
Yeah, there.
Okay. All right. So I do want to talk about one more thing before we move on to the next section here. Another thing that we talk about for being able to count things is arrangements where you've got indistinguishable objects. So for example, maybe I ask you to say, what's the arrangements of the letters in the word Mississippi? This one I think is just more about just doing it rather than thinking about a formula necessarily. Okay. Notice that if I say, for example, right now, flip the 2 P's around, does that look different? No. So what we're interested in is distinguishable arrangements, if you will. Right? Well, I've got some repeated letters. Well, what if they were all different? Well, if the letters were all different, how many arrangements would you have? If the letters are all different, how many arrangements would you have? 11 factorial, because there's 11 things in there, right? 11 letters. But what should we divide this out by, do you think? Well, I just said, for example, if the 2 P's are indistinguishable, I could rearrange, once the P's are set, I could rearrange those P's and I can't tell the difference. So what one thing do you think we should divide out by if I'm just considering the P's? 2 factorial, right? Because there's 2 ways to rearrange the P's. What else do we have issues with distinguishing with? S's. How many S's are there? So once you set the S's, how many different ways are there to rearrange the S's? 4 factorial, right? What else are we going to have a trouble with distinguishing? You have the 4 I's, so you divide by the 4 factorial there. There's only one M, but if I wanted to finish this off nicely, I could also do a 1 factorial. These numbers, when you add them together here, 2 plus 4 plus 4 plus 1 should equal your total. So if you've got indistinguishable objects like this, but you want distinct arrangements, you're going to divide out by the number of ways to rearrange your indistinguishable things. Okay. Does that make sense? So as another example, just real quick, like I said, I want to go just start conditional probability in a minute. In your text, they have a problem. This is 1.2-11. They've got 3 students and 6 faculty to be seated at a table. Now, if I want to treat, which I should, if I want to treat everybody as distinguishable, as 9 different people, how many total arrangements are there at the table? Good. Right? I've got 9 different people, correct? I've got 9 different people, and I want to seat them at a table. There's 9 factorial different ways to do that, correct? But what if we're looking at, is rather than treating them as separate people, what if we only worry about arrangements that don't distinguish, if I can spell, different students and don't distinguish different faculty. What I mean by that, maybe if I put all 3 students at the front, doesn't matter how I rearrange the student, or sorry, at the left-hand side. I put all 3 students at the left-hand side. Doesn't matter how I arrange them, they're still just students on the left, faculty on the right. Does that make sense? Okay. So that would be, again, I could think about, if I think about just letters, I could have 3 students, 6 faculty. And this looks like that Mississippi example, doesn't it? So what would we have? Well, we know 9 factorial was the total. What would you divide out by in this case? 3 factorial and 6 factorial. Does that make sense? Because again, I'm thinking about, I'm not worried about who the individuals are. I'm just looking at where are the students seated versus where are the faculty seated. Does that make sense? So that's indistinguishable objects. So for homework, and then like I said, we're going to start conditional probability real quick. For homework, and this will be due next Tuesday, which is the 4th. This is after section 1.2, and I want you to do 4, 9, and 11. Since you told me that you don't have page numbers, so page numbers don't help if you have the electronic book. All right. So conditional probability. And I asked you to watch the video ahead of time. What conditional probability really does is if you're given some additional information before you try to calculate a probability. So you know one thing happened. You're trying to figure out additional information about the one thing that happened. So, for example, let's say you draw a card out of a deck. The probability of drawing that one card is 1 out of 52, right? If you draw a single card. But if you know that, for example, you drew a heart, you knew that the card was a heart, you're not worried about the other 49 cards in the deck anymore, right? You're just worried about that out of that the hearts, what happened, right? So, say for example, the probability that you drew the 4 of hearts is 1 out of 52, but given that it's a heart, the probability that you drew the 4 of hearts is 1 out of 13. Then, okay? So your conditional probability gives you that additional information that allows you to change the size of your sample space. So, in general, we write the probability of, we say A given B. So this is written, we read that vertical bar as given. Well, what has to happen? Well, if you're doing the A given B, well, the B is the given information. So that's when we're going to change the size of our sample space. So as long as B is not impossible, because we don't want to divide by 0, okay? The B is the given information, so that's what goes here. Okay? Now, given that B happened, we also want A to happen. Okay? So this is why it's not just probability of A on top, because A may happen without B happening. Okay? So on top, we're going to do A and B. If you think about it from counting perspective, again, having given information changes the size of your sample space. You have just the number of ways that B can happen, but we also need A to happen at the exact same time, right? So that's what we need to make sure we count both A and B at the same time. All right, so let's see if we can do a quick problem with this. So I got some extra problems here to work on as we go along here. All right, so let's look at that first one real quick, and we'll do more of these next time. I can scroll over to the top. All right. We've got probability of A is 1/6. The probability of B is 5/12. They tell you the probability of a couple of different conditional probabilities. When you add them together, you get 7/10. And it asks for the probability of A intersect B. All right, so before we do anything else, let's look at those two pieces. So the first part here says probability of A given B. Well, we just said a second ago, how can we rewrite that? What's the formula say how we can rewrite that? Good, that'd be divided by the probability of B, all right? So if we switch it around, if we do probability of B given A, how's that going to be? Good. Be probability. I mean, if I literally just plug in the different pieces in the formula, you'd have probability of B intersect A over probability of A. Remember, the given information was what goes in the denominator. All right. What I want to notice here, though, is, are these numerators really different? No. A and B, B and A, same thing, right? Okay. So if I go back up to my formula here, or sorry, not my formula, my equation that they give us, you'd have probability of A intersect B over 5/12, right? So I'm just plugging that in there. We'd have probability of A intersect B over 1/6. That has to equal 7/10. Does that look like an equation you can solve? It's got fractions in it, but you can certainly solve that, right? Okay. So this one is just a matter of playing around with the formulas and solving the equation. So one thing we want to notice, by the way, is and we're going to talk about this more in the coming sections, notice that I've got my probability of A intersect B in both spots. Notice that you kind of got this, well, you've got a nice relationship that I can kind of use this property here to reverse what I'm given, if you will. Right? So I've got, here my given B, here my given A. So I flip-flop things. We're going to talk about Bayes' theorem in a couple of sections. Basically, Bayes' theorem talks about something like along the lines of, you know how accurate a test is for a given disease. Okay? But maybe that disease is very rare. So you're not very likely to have it to start with. But you come up and tested positive. The idea behind, so that would be the given part, right? Given that you're positive, what's the probability that you have the disease? Well, you know it the other way around. if you have the disease, you know what the probability is that you tested positive, how good the test is. You can flip things around to help you calculate that probability. We're going to talk about that later. That's what Bayes' theorem's about. It's all about this relationship here about how you can flip-flop the given. All right? Given that you tested positive, you want to know what the disease is. That might be important to you. And you know how accurate a test is. And so then you can flip-flop things around to help you with probabilities. Like I said, we'll talk about that later. So we'll do more conditional probabilities next time. Otherwise, have a good one. We'll see you on Thursday, if not before. If you always need to talk to me before, you know where to find me. Some of you I'll see tomorrow because you have me in class. You get to see me every single day.